Hello there. In this video we're going to continue our discussions of exponential and logarithmic functions by considering how to solve exponential equations. So as we already know, we should be able to solve basic equations such as x plus 5 is equal to 2 and x squared is equal to 4. For example, for x plus 5 is equal to 2, we usually apply subtraction to both sides of this equation, so subtract both sides by 5, and we're going to get that x is equal to minus 3. For the quadratic equation, typically we're going to apply the inverse of squaring, which is usually the principal square root. So that's going to give us the absolute value of x is going to be equal to 2. And then from absolute value equations, we usually get that x is equal to 2 or x is equal to negative 2. So in this video, we're going to be focusing on what we call exponential equations, where we have the variable in the exponent of our expression. So, in order to solve equations such as 2 to the power of x is equal to 5, we need a very basic principle in order to sort of develop the idea of what is the inverse of exponentiating by 2. Right? And that is this. So the inverse of exponentials are logarithms. So remember, one of the basic properties associated with logarithms and exponentials is the following representation. In particular, that the log base a of a to the power of x is going to be equal to x. Right? So we're going to use this property in order to solve these equations. So let us bring back that little example. So example 1, suppose we have 2 to the power of x is equal to 5. So we have an exponential function with a base of 2. So we need to introduce a logarithm with a base of 2 to both sides of this equation. So I'm going to take the log base 2 of both sides of this equation. So we have log base 2 of 2 to the x is going to be equal to the log base 2 of 5. So as we already know, the log base 2 of 2 to the x, so those cancel. So we're just going to be left with x is going to be equal to the log base 2 of 5. So that's going to be your solution. In general, we can extend this quite easily. So consider the general equation, a to the x is equal to b. So I'm going to apply a logarithm base a of both sides. So we're going to take the log base a of the left and the log base a of the right-hand side. So as we already know, the left-hand side just reduces to x, and the right-hand side is just equal to the log base a of b. Right? And here we see a restriction on the value of b, so b must be greater than 0 in order for this to be a real number. Also keep in mind, we can write this solution in terms of natural logarithms by using our change of base. So this is equivalent to writing x is equal to the natural log of b, all divided by the natural log of a. Right? So those are equivalent ways of saying the same exact thing. So let's introduce a more in-depth equation, still not too difficult. 3e to the power of x minus 5 is equal to 7. So we're going to begin by isolating this equation for this exponential term, and that's going to give us 3e to the x is equal to 12, which means e to the x must be equal to 4. So I'm going to introduce a log base e of both sides. So log base e of e to the x is going to be equal to the log base e of 4. But remember that the log base e actually has a special name, that is the natural logarithm. So this is actually equivalent to taking the natural log of both sides of this equation. Right? So the natural log of e to the x is just equal to x. So we have that x is just equal to the natural log of 4. So that's our solution. Let's do a few more examples that are a little bit more involved. So example 4. Suppose we have negative 14 plus 5 to the power negative x over 2 plus 1 is all equal to minus 13. So I'm going to begin by adding 14 to both sides. So that's going to give us 5 to the power negative x over 2. So negative x over 2 plus 1 is going to be equal to 1. And then I'm going to get rid of this base of 5. So I'm going to introduce a log base 5 of both sides. So log base 5 of 5 to the negative x over 2 plus 1 is equal to the log base 5 of 1. So as we already know, these cancel. And we're just going to be left with negative x over 2 plus 1 is equal to, and that is a special number, that's just equal to 0. Right? Because 5 to the power of 0 is equal to 1. right? So I'm going to negate both sides by 1. So we have negative x over 2 is equal to minus 1. And then we get that our solution is going to be x is equal to 2. So that's our solution. So another more fun equation. So let us assume we have e to the power of 2x minus 5e to the power of x plus 6 is equal to 0. So you should be able to notice that this is pretty much like a quadratic equation, so I'm going to transform it into such. I'm going to let u be equal to e to the x, so I'm going to use substitution. So once I do that, we're going to have that this is going to be the same as u squared minus 5u plus 6 is equal to 0, and then I can factor this. So I'm going to have u minus 6, and actually no, let's do u minus 3 and u minus 2 is equal to 0. Actually, you know what? I'm going to make this problem a little bit more different. I'm going to change this plus. I'm going to change it to a minus sign. Right? And you'll see why I want to explore this problem. This problem is a little bit more interesting, actually. So if I factor this, so the factoring actually doesn't really change much. So we're still going to have a u minus 6, and then we're going to have u plus 1, and that's going to be equal to 0. Right? So we have two solutions, either u is equal to 6 or u is equal to negative 1. So then I'm going to go back in terms of u and I'm going to replace. So I have e to the x is equal to 6 or e to the x is equal to negative 1. And then we can solve each of these baby exponential equations, right? So I'm going to take the log of the first one. So we have the natural log of e to the x is equal to the natural log of 6, or the natural log of e to the x must be equal to the natural log of minus 1, right? So the left-hand side is just nice. So that's going to be x is equal to the natural log of 6, and the right-hand side is going to be equal to x is equal to the natural log of negative 1. But as we already know, negative 1 is not in the domain of the function natural log of x, right? F of x is equal to the natural log of x, because x must be greater than 0, right? So this number here is not in the set of reals, right? It's actually in the set of complex numbers, but we're not going to talk about that now. So therefore, we only have one real solution, and that's going to be negative the natural log of 6. So let's look at a more general example. So let's consider the function a is equal to p times 1 plus r over n to the nt. So this is going to be related to an application we'll do a little bit later. And let's solve this equation for t, right? In terms of all of these other variables, n, r, p, and a. So the first thing I'm going to do is try and get this exponential term by itself. So that's going to give me 1 plus r over n to the nt is going to be equal to a divided by p. I don't really want to do a log base 1 plus r over n. That's a little bit nasty. So what I'm actually going to do is I'm just going to do a natural log of both sides of this. So I'm going to do the natural log of 1 plus r over m to the nt, and that's going to be equal to the natural log of a over p. Okay, so remember the power rule for logarithms. This nt can actually come down. So that's going to give us nt times the natural log of 1 plus r over n, and that's going to be equal to the natural log of a over p. So we're solving for t, and this term doesn't have any t's in it. And we also have this n hanging out as well. So we can actually divide both sides by n natural log of 1 plus r over n to get our value for t. So t is going to be equal to 1 over n times the natural log of a over r, all divided by the natural log of 1 plus r over n, right? And that is, that's a p actually, right? Yeah, almost looks like an r, so that's actually a p. Right, so let's just change that. Right, and that is our solution in terms of t. And one last example that we can sort of tie in with exponential functions. So suppose f of x is equal to the exponential function 6e to the 1 minus x minus 4. So find the x-intercepts of f. So the x-intercepts are when this function is equal to 0. So if f of x is equal to 0, this is going to imply that 0 must be equal to 6e to the 1 minus x minus 4. So that means e to the 1 minus x must be equal to 4 divided by 6, which is going to be the same as 2/3. I'm then going to introduce a logarithm, natural logarithm to both sides. So the natural log of e to the 1 minus x is going to be equal to the natural log of 2/3. And then I can just cancel out the natural log and e here because they're inverses. So then I'm just going to be left with 1 minus x is going to be equal to the natural log of 2/3. So 1 minus x is equal to that, so I can easily solve for x. So that means x is going to be equal to 1 minus the natural log of 2/3, right? So remember that the 2/3 is between 0 and 1, so the natural log of 2/3 is going to be a negative number. So this is actually 1 plus some positive number. And actually you can find that the numerical value is approximately 1.05. So that means what? So that means the x-intercept, so the x-intercept for this particular function is going to be approximately 1.405, 0, or more exactly, 1 minus the natural log of 2/3, 0. Okay? So solving exponential equations in general are not that complicated. Of course, you can make it complicated by introducing other functions like rationals and such. But this is just the basics. We'll get into more complicated functions and equations a little bit later. Anyway, this is just an intro to solving exponential equations. Hope you enjoyed. As always, if you enjoyed, please like this video, consider leaving a comment, and if you enjoy the channel content, please subscribe. We publish several new topics every single week. Thank you.